Okay, so let's talk about this review sheet. First problem was the one with the train car with the uh, little gun that shoots the rubber balls on it, right? So here is a picture of the train car, and what we've got is this gun at one end, and we start with all the balls in one spot at one end, and the gun shoots them to the other end, and the rate of fire is specified and all that. And I'm going to try to draw something roughly the same size here. And all the balls end up at the other end. Okay. And at that point, the balls have gone from basically the distance between the starting point of the balls and the final point of the ball, final position of the balls on the train cart is I think 30 meters if I recall correctly. So let me see if this will. Okay, there we go. So basically from here to here is 30 meters. Okay, so, and this is where everything is initially, okay? At the end, or what we call the end of the problem, is really 60 seconds after you started shooting these balls. And so what's really important here is that it's enough time for all the balls to go from here to here. The rate of fire of the gun, what did I say? It was like 200 balls per second, and there are 6,000 balls. So it only takes 30 seconds to fire all the balls and run out of ammunition, right? And then, another third of the second for the last ball to get down to the basket and fall in. So, after 31 seconds, definitely all the balls are in the basket. And after 60 seconds, even if they were bouncing around a little, they're all, they've all settled in by the end. Okay? So what's important here, and people will do all kinds of fancy things where they try to find the average force or the recoil force on the gun as it shoots the balls, and how many balls are in the air at once, how fast are they going. But this is really a much simpler problem than most people make it. To figure this out, what you have to do is look at the whole system. So these are my two states of the system here. This is the initial state, this is the final state. And what I want to do is look at, really the key is, what does the center of mass do? Okay, so let's start by just saying, look, at the beginning, when all the balls are in the in the gun, then the center of mass of this system is going to be somewhere to the left of the center of the train. Okay, if you think like the train car, what did I say? The balls had a mass of 600 kilograms. Okay, and then the train car, what's left of the train car, besides the balls, has 1,200 kilograms of mass. Wait, it was 600 or 6,000? 600, right. And then this is a mass of 1,200 kilograms. Okay, so, and then down here, 1,200 kilograms for the train car and 600 kilograms for the balls. Okay, so mass of the car is 1,200 kilograms. Mass of the balls is 600 kilograms. Okay, so what do we know? We know at the beginning everything is at rest. Okay, so the velocity of the train car is equal to the velocity of the balls, which is equal to 0. Here at the end, we at least know that all the balls have fallen in the basket, so they must all have the same velocity as the train car. So we can treat the balls as just one object with this mass, and it has the same velocity as the train car, whatever that is. The balls are only moving because they're in the basket traveling with the train car, right? So, what is the initial velocity of this is 0, which means, well, the key here is to realize there are no external forces acting on this system, okay? There are no net external forces, okay? The sum of external forces on the system is 0, okay? Nothing's pushing, nothing's pulling, and gravity is balanced out by normal forces and all. So the sum of external forces on the system is 0. And the sum of external forces is equal to the mass of the system, total, times the acceleration of the system's center of mass. Now, what this means, if the sum of external forces is 0, then the acceleration of the center of mass must also be 0. So the center of mass of the system is not moving. It's not accelerating. Let's start with that. It's not accelerating, which means it has a constant velocity, okay? So that means that velocity of the center of mass must be constant. Okay, so what's the velocity of the center of mass here? Well, this is not very hard, right? Because the velocity of the center of mass is the velocity of the center of mass of the system is equal to the total momentum of the system over the total mass of the system. Okay, well, what's the total momentum of the system beginning is 0, because at the beginning, before you start firing the gun, nothing's moving. So it doesn't matter what the total mass is. Total momentum of the system, the beginning is 0. Okay, so total momentum here. Well, actually, I'm just going to make it a scalar since we're only concerned with the x momentum. The horizontal momentum is 0. So this means the velocity of the center mass must be 0. And we just showed the velocity of center mass is constant. This here applies all the time. There are never external forces acting on this system from the beginning to the end, and at all points in between, there are no external forces acting. So the velocity of the center mass of the system is constant, which means that the velocity of the center mass is 0 here. It must also be 0 here. Okay? So what we've shown now, first of all, the acceleration of the center mass of the system is 0. And so, let's see. Right, so we show the velocity of the center mass is 0 here. We've also shown, let's see, no external forces acting on it. The acceleration of the center mass must be 0 here. And since this is a case where these guys have the same acceleration, which is going to be the same as the center mass acceleration, it's 0. I think it's pretty obvious that the acceleration is 0 at the end, but I just wanted to, sort of make that clear. So part A, the answer is 0. Okay. Part B, what's the velocity of the train car at the end? Well, velocity of the train car is equal to the velocity of the balls, and they're both the same, so they must be equal to the velocity of center mass, which is, we showed 0. So the answer to B is also 0. C is the only one that is a little tricky, and what happens here is that basically if you take a, let me see if I can try to do this again. Let's take a, that's the balls, and that's the train car at the beginning. So initially what you've got is you got the train car. Let's say the train car center is right there. We don't really know exactly where it is. We don't care, but and the balls are right there. So the center of the train car is there, and let's say it's the center of the train car. It's also the center of mass. Let's see, what's a better way to show this? Tell you what I want to do is I'm going to start from the fact that the train car, the center of mass of the system does not get displaced. So the center of mass of the system always has 0 velocity. Okay. So the velocity of the center mass is constant. Velocity of the center mass equals 0 always throughout this whole thing, which means that over any stretch of time, including from t equals 0 to t equals 60 seconds, the change in position of the center mass is 0. That doesn't mean the change in or the displacement of the train car is 0, because the train car could get displaced and the balls could get displaced in such a way that the center of mass goes through no net displacement. So I'm going to take this equation here and say the mass of the balls times the displacement the balls go through plus the mass of the train car times the displacement the train car goes through is equal to the total mass of the two times the displacement of the center of mass. Okay, so what happens is the balls now move 30 meters relative to the train car, which means that delta x for the balls equals delta x for the car plus 30 meters. Okay, and so we plug this in. Whatever displacement the train car goes through, the balls go through the same displacement, plus they get shifted 30 meters to the right. And I'm taking the right as positive x. So all this is a fancy way of basically getting to plug in this for this, and what we get is mb times delta x for the train car, okay, plus mb times 30 meters, plus mc times delta x for the train car, equals mb plus mc times delta x for the center mass. Except we just said delta x for the center mass is 0, right? So we can actually just make this 0. Okay, so what we get now is mb plus mc times delta xc plus mb times 30 meters equals 0. So now let's see, where does this get us? This gets us that we take, well, we can just say mb plus mc is 1,800 kilograms. mb is 600 kilograms. So when we divide this through, this becomes a 1/3. So the long and short of it is that delta x, the displacement of the train car, is going to be negative, negative 10 meters. Okay. What happens is the train car moves 10 meters to the left, and the balls move 20 meters to the right. So the balls have displaced a net 30 meters relative to the train car. And those two motions keep the center of mass at the same place. So let me just, let's see. Let me just show you sort of what it would look like from the ground. So to make this perfectly clear if you're not getting this. So here's the ground. Initially, you're going to have the train car like this and all the balls down at this end. And the center of mass will be roughly right here. Something like that, okay? Now later, the center of mass is at the same spot. But now the train car extends a bit more, a bit more to the left than it did before, okay? So the train car has shifted this way 10 meters, and the balls have the train car has shifted to the left 10 meters, and the balls have shifted to the right, shifted to the right 20 meters. It's not to scale, but whatever. But the center of mass has stayed in the same place. So kind of a scattershot explanation. I hope that helps, though.